So continuing where we left off, we're now going to learn about how compounds form. And again, this really has to do with an interaction of the electrons that are present on the outermost part of an atom. And we call these valence electrons. So I'm going to show you this little video because I think it helps kind of understand how that happens. So let me pop that open.
The noble gases. Where does that term noble gases come from? Are they nobility? Do they rush to rescue maidens?
No, you're thinking of heroes. They're like nobility in the sense that they don't mix with the riffraff. They don't like to react with any other elements. By and large, it's not possible to form compounds with them.
Well, it's a shame for your collection that they're gases because you've got big blanks here. Oh, ho, ho, ho. The noble gases, like neon and argon, pose a problem for chemists who prefer their elements to join forces and react with each other. You can run an electric current through them, excite their electrons, and get pretty colors, which is how neon lights work. But the noble gases don't react. They pretty much refuse to combine with other elements.
Being an inert gas, being unwilling to mix with the other elements, react with them, this is a very clear-cut distinction that sets apart this particular column from all the others in the periodic table.
So why are these guys so aloof? As it turns out, protons may determine the identity of an element, but electrons rule its reactivity. And reactivity is a shell game. Here's how the game is played. Imagine that these balls are electrons, and the target is an atom. Electrons don't just pile on around the nucleus. As with skee-ball, where you land relative to the center counts.
Oh, come on!
The electrons take up positions in what can be thought of as concentric shells. The first shell maxes out at just 2 electrons. The next holds 8, then it goes up to 18. An atom with 8 electrons in its outer shell makes one happy, satisfied atom. And noble gases come pre-equipped with completely satisfied shells. And is this the only column like that?
It's the only column where all the shells are completely filled.
But what about the column just before those stable noble gases? They're called the halogens. They have an outer shell that needs just one more electron to be full, and they'll grab it any way they can. The group includes fluorine and bromine, but the most notorious is chlorine. 17 protons, surrounded by 17 electrons, arranged in 3 shells of 2, 8, and 7, one short of being full. It's that extra electron chlorine will get any way it can, sometimes with violent results. That's why chlorine gas was used as a deadly poison in World War I.
Chlorine, I mean, this is nasty stuff. This will take electrons from kittens. You know, it'll go and steal an electron off the water in your lungs and turn it to hydrochloric acid because it really wants an electron.
Yeah, maybe I'll leave that where it was.
Now, if you go the other direction, you end up with the alkali metals.
The alkali metals are the first column. Each of them has full shells plus one extra electron sitting in a new outer shell. They have familiar names like lithium, sodium, and potassium. And they all want to get rid of that single lonely electron any way they can.
Okay, so hopefully that gave you a little bit better picture of how electrons kind of interact with other elements. And again, the ones in the outermost shell, as shown here, are the valence electrons. So the goal is to get to that magic number of 8. Unless you're on the very, very inside, then that's a unique situation where there's only 2. But normally speaking, you would want to have 8. And so elements are going to do pretty much anything they can to get to that number of 8. So let's, which introduces the idea of something called electronegativity. And electronegativity, as I will show you in a bit, is really the strength of the pull that one element has on any other in terms of electrons. So something that's really, really electronegative has a really strong pull on electrons. So that chlorine, for example, in the video that they were talking about, has 7 already in its outer shell, and it only needs 1 more. So it's going to be super strong. It's going to do anything it can to pull that 1 more. If it's willing to give up electrons, then it's super low in terms of electronegativity because it doesn't even want to pull electrons. It actually wants to give them away. So that's kind of the low end of the spectrum. And so this leads to instances where some elements are just going to give away their electrons, some elements are going to steal electrons, and there's a third category that we'll learn about where atoms just share. So if there's not one that's really stronger than the other, one can't win out over the other, so they end up sharing. So here's kind of a picture of what that electronegativity piece looks like. You can see that, let's see, here, there's a super low electronegativity down here in the bottom of the left side, and then it increases as you go across. So as you move across in the same row, it's going to become more and more electronegative. And that's because the elements in the first row only have kind of 1 valence electron, so they want to give it away. But as you move across, these elements have more and more electrons in their outer shell, so they end up wanting to complete it more than the ones on the left. And it also increases as you go up. So F over here, or fluorine, is super electronegative, whereas FR was not. So if you kind of know the difference in electronegativity, you can get a sense of what elements might be taking electrons and what elements might be losing electrons. Okay, so here is just a chart for you. You would never have to know these numbers, but it gives you an idea of where electronegativity falls. So F has 4, which if you look comparatively at all the numbers in the chart is really high, and then down here is really low. Remembering hydrogen is kind of weird. It's over here, but most of the time it's actually a gas, so it kind of, in fake world, lives over here, but it is where it is. So that's kind of a unique situation, but you would always be given these numbers to help you. So let's look, for example, at a practice. We have hydrogen and chlorine. So what we need to do in order to solve this problem is basically figure out what the numbers are for each and then subtract and figure out what the difference is. So it's essentially a math problem. So hydrogen and chlorine. So if I look at where those live on the chart, hydrogen is up over here on the left at 2.1, and chlorine is over here on the right at 3. So in order to figure it out, you're going to want to take the higher number minus the lower number. So let me go to the next slide and figure out where we were here. So we had hydrogen at 2.1 and we had chlorine at 3. So to figure out the electronegativity, you would just take 3 minus 2.1 and you would get 0.9. Sorry for the kindergartner handwriting here. So that's kind of our electronegativity difference. Great, we have a number, but what does that even mean? In order to figure that out, there's a chart to help you. If the number is really small, then that means that there is no real difference in electronegativity. So they end up having to share. If it's somewhere in the middle, then there's sharing going on, but it's not really an equal sharing. Oh, let's fix that. In the sense of one of them is going to pull a little bit stronger, but it's not enough to steal an electron away. If you get to the high end, where there's a really strong difference in electronegativity, then you actually end up having the atom steal from the weaker one. So since ours was 0.9, it falls into this middle category, and we'll learn about that a little bit later. So here we go, practicing classifying. So in this instance, you're going to want to figure out what those specific electronegativities are, and then you can apply them to this situation. So for the first problem, we have hydrogen and iodine. And then we're going to have hydrogen and oxygen, we're going to have sodium and chlorine, and we're going to have oxygen and oxygen. So take a moment. We're going to go back to our chart here, and I want you to record what those numbers are in terms of electronegativity. So take a moment to do that now while I do that as well, and then you can use those when we get back to the other slide. Chlorine. All right. So I have written them down, and we're going to kind of go back and do this together. So looking at how this would work, again, hydrogen, as we learned from the previous example, is at 2.1. Iodine, if you looked at the chart, you can always go back if you need, is 2.5. So then the difference would be 2.5 minus 2.1. So doing some math here, that's 0.4. Hydrogen and oxygen, well, hydrogen was 2.1. Oxygen, if you look at the chart, is 3.5. So doing some math in your head or in your calculator, 3.5 minus 2.1 is 1.4. Sodium is, 0.9. That was really bad. And chlorine is 3. So 3 minus 0.9 ends up being 2.1. And oxygen, well, anytime you have two elements together that are the same, two atoms of the same element together, well, then they're always going to end up being 0, because one oxygen is no stronger than another. So it's always going to end up having that 0. So using that chart that we had on the last slide, you can determine whether or not they're sharing or sharing unequally, or one is stealing more so than the other. So for example, here in this one, number 3, sodium and chlorine, it passes that tipping point. So in that situation, chlorine would end up stealing an electron away from sodium. So what do we call this? We call it an ionic bond. When one atom steals from another atom, we call it ionic bonding. And we're going to go through examples and types of what that looks like. If they have to share, then we're going to call it covalent bonding. So we will dive into that on the next slide. And remember, here's kind of the distinction of which category it falls into. So we're going to practice naming when we get to the next presentation.